Alright, here's another problem where it's interesting idea, but sort of a strange proof. But anyways, so suppose U is in R has multiple right inverses, then U has no left inverse. Because if it did, then the left inverse and the right inverse would be the same, and it'd be the inverse, and then it'd be unique. And so that's why we know that. Let UA equal 1. So then obviously U is not 0. So given N and M, here, for all N and N, define an element AN to be 1 minus AU, U to the N plus A, which is in, let's see here, this is in the ring, because it's just, you just combine a bunch of stuff. I guess this doesn't really use the fact that U is non-zero. At first I was thinking, oh, if we want N to be allowed to be 0, then you would have to make sure that U is not 0 because you can't have 0 to the 0, but whatever. I'm not going to go back and make it neater. I claim that the sequence of ANs where N runs over all the natural numbers is countable. To this end, let N and M be natural numbers such that, and then without loss of generality, we're going to say N is greater than M. So, see here then. Man, this is really big font, but it should work. 1 minus A U. Let's see here. ANU is not 1. Because U does not have a right inverse. Or no, U does not have a left inverse. And so what does that mean? Let's expand this out. So 1 minus AU, this is U to the... Oh, no. We don't want to do that yet. Then 1 minus AU to the times U to the N minus M minus 1 plus A. This whole thing times U is not equal to 1, i.e. 1 minus AU, U to the N, God, my U's and my N's, N, right, plus AU is not equal to 1, i.e. 1 minus AU, U to the N minus M is not equal to 1 minus AU. And then, what is this? i.e. 1 minus AU, U to the N plus A is not equal to 1 minus A, U to the M plus A, i.e. AN is not equal to AM. However, for all n and n, or here, so thus an is countable. Now for all n and n, what do we have? We want to compute UAN. That's u times 1 minus AU, u to the n plus a, which is u 1 minus AU, u to the n plus UA. Well, this is just going to be, if you distribute the 1 inside the parentheses, you get u minus UAU times u to the n plus 1. And of course the UA on the inside, that becomes a 1, and so that becomes a 0, so this is equal to 1. So AN is a right inverse. Hence, U has at least countably many right inverses. And so that's a little bit of a weird proof, because like, how would you have come up with that element in the first place? And furthermore, the thing I was thinking beforehand was like, oh, well, we suppose that it has multiple different things. And so I was thinking, oh, well, let's take suppose that it has multiple right inverses and prove that it has countably many. I was thinking, oh, well, maybe you could take two right inverses and sort of do some sort of linear combination of them, or just something you can do with them to generate countably many right inverses. But it didn't work, and then I looked online and they were just like, oh, just use this as the element. So I don't know, I guess someone just got lucky one day and was like, oh, let's try this, and it worked. Yeah, not my favorite type of problem, but anyways. So what's the next part? The next part is to prove this does not hold in monoids, or for monoids in general. Let M be the monoid generated by 3 elements A, B, and C, with relation AB equals AC equals E. So M basically consists of words of finite length, and consisting of letters A, B, and C, but the words are such that the sequence AB and the sequence AC do not appear in the words. So if you have a word in M, and you look at the sequence of letters, you cannot look in there and find the sequence A. You cannot find an A followed by a B, and you cannot find an A followed by a C, because it would just be the identity, and they would not be included. So anyways, then A has 2 right inverses and no left inverse. And that's because if you just have an A, then you can't put anything to the left of it to cancel out with that A, and obviously A, B, and AC both cancel out. The other thing, of course, this is a this is a monoid, and the operation is concatenation. And E is just like the empty string, and you can kind of convince yourself that this is indeed a monoid. It's not too difficult. You concatenate 2 words, you get a word. You concatenate a word with the empty string, and you'll get what you started with, and that's all you need. So there you go. This completes our proof.